Over a year. That's how long it's been since SpaceX last caught a booster mid-air. 450 days. No catch. Nothing. And yet, SpaceX just revealed Booster Vive 3. The most advanced Super Heavy ever built. Completely redesigned. From the engines, to the fins, to the arms that grab it out of the sky. 3 grid fins instead of 4. Catch points built directly into the fins themselves. Electromechanical arms replacing hydraulics. Faster, sharper, more precise. This isn't an upgrade. This is a reinvention. So why does it matter right now? Because SpaceX President Gwynne Shotwell just confirmed major milestones are coming within months of Flight 13. The next catch attempt could arrive with almost zero warning. The question isn't whether SpaceX can catch a booster. They already proved that. The question is, can Booster Vive 3 make it routine? Stay with me. Because what changed is bigger than most people realize. Let's go back to the last time it happened. Flight 8, October 2024. A 70-meter-tall steel rocket, weighing hundreds of tons, fell from the sky at nearly 200 miles per hour, and instead of crashing into the ocean, it was caught mid-air by 2 giant robotic arms attached to a launch tower. The crowd went insane. Engineers were crying. Even people who had never watched a rocket launch in their lives stopped and stared at their screens. Because what they just watched shouldn't have been possible. For 60 years, the only options for recovering a rocket were simple: splash it into the ocean or land it on a pad. That's it. That was the limit of human engineering. SpaceX looked at both options and said, no. We're going to grab it out of the sky. And they did. But here's what most people don't talk about. Since Flight 8, not a single successful booster catch. Flight 9, no catch. Flight 10, no catch. Flight 11, no catch. Flight 12, the booster didn't even make it back in one piece. 4 flights, 0 catches. So the question burning through the SpaceX community right now is simple. What went wrong? And more importantly, what has SpaceX been doing for the past 450 days to fix it? The answer involves a complete redesign, a new generation of vehicle, and a level of engineering ambition that makes even the original catch look modest. That vehicle is Booster Vive 3. And what SpaceX just revealed about it changes everything. What actually happened after Flight 8, the problems nobody talks about. Here's the part most YouTube channels skip over. After the celebration of Flight 8's successful catch faded, SpaceX engineers sat down and looked at the data, and what they found was uncomfortable. The catch worked, but it worked in a way that exposed serious vulnerabilities. The original grid fins, 4 of them positioned high on the booster, were taking catastrophic heat damage during hot staging. Hot staging is the moment when the upper stage Raptor engines ignite while the booster is still connected. It's violent, it's fast, and it sprays superheated exhaust directly onto the booster's upper section. Think of it like lighting a blowtorch and pointing it directly at the part of your rocket you need to use as a handle. Every single flight, the fins were being cooked. On top of that, the catch points, the physical hooks that Mechazilla's arms grab onto, were separate hardware attached to the booster's structure. Separate components mean separate failure points. More weight, more complexity, more things that can go wrong at exactly the wrong moment. And then there were the chopsticks themselves. The original hydraulic arms were powerful, but hydraulics have a fundamental problem. They're slow to respond and difficult to fine-tune. When you're trying to catch a skyscraper-sized rocket that's moving and swaying and compensating for wind, milliseconds matter. A hydraulic system that responds a fraction of a second late isn't just inefficient. It could mean the difference between a perfect catch and a catastrophic miss. Flight 12 made all of this brutally clear. A Raptor engine failed shortly after launch. The boost-back sequence, the critical burn that reverses the booster's direction and sends it back toward the launch site, showed irregular behavior. The landing burn was delayed, and the booster never made it back, and SpaceX still hadn't solved the fundamental reliability problem. So they went back to the drawing board, not to patch the existing design, to replace it entirely. Booster Vive 3, the complete redesign nobody saw coming. This is where it gets genuinely fascinating. When SpaceX revealed the full scope of Booster Vive 3's changes, even experienced aerospace engineers did a double take. Because V3 isn't an upgrade, it's a ground-up rethink of what a reusable booster should look like. Start with the most visible change, the grid fins. V3 has 3 fins instead of 4. At first glance, that sounds like a downgrade. Fewer fins, less control, right? Wrong. Completely wrong. Here's why. In engineering, removing a component is often more valuable than adding one. Every part you eliminate is a part that can't fail. Every kilogram you remove is a kilogram your engines don't have to lift. Every simplified system is a system that's easier to inspect, easier to maintain, and faster to turn around. SpaceX didn't go from 4 fins to 3 to save money. They did it because 3 larger, stronger, better positioned fins outperform 4 smaller ones in every metric that matters for recovery. But the real innovation isn't the number of fins. It's what those fins now do. SpaceX integrated the catch points directly into 2 of the 3 fins. That's not a small change. That's a fundamental rethinking of how the catch system works. Previously, the catch points were separate brackets bolted onto the booster's exterior. They added weight, they added drag, they were exposed to heat and stress during every phase of flight, and they created a structural complexity that made precision catches harder. Now, when Mechazilla's arms close around the booster, they're gripping the fins. The same structures that steer the vehicle during descent are also the structures that absorb the catch force. The result? Better force distribution, less structural stress, lower mass, and a catch that's inherently more stable because the grip point and the control surface are the same object. It's elegant, brutally, beautifully elegant. And the fins aren't just redesigned, they're repositioned. V3 moves the fins lower, away from the hottest zone during hot staging. Less heat, less damage. Problem solved. The engine revolution hiding inside V3. The engine story inside V3 is more significant than most people realize. Every previous booster used Raptor 2 engines. Powerful, yes, but complex, maintenance intensive, and in Flight 12 one of them failed shortly after launch, a failure that cascaded into the boostback issues that ultimately doomed the recovery attempt. One engine, one failure, one lost booster. That's the fragility problem SpaceX is trying to solve. V3 introduces the latest generation Raptors, engines that are simultaneously more powerful and simpler than their predecessors. That combination sounds contradictory. More power but simpler? How? The answer lies in what SpaceX learned from thousands of engine test firings and multiple flights worth of real-world data. They identified which components were adding complexity without adding value. They redesigned combustion chamber geometries. They refined manufacturing processes to eliminate tolerance variations that caused inconsistent performance. The result is an engine that produces more thrust, burns more efficiently, and has fewer parts that can fail at the worst possible moment. But here's the detail that's crucial for the catch attempt specifically. During the final seconds before catch, when the booster is hovering 30 to 40 meters above the ground, descending at a precisely calculated rate, the engines are making thousands of micro adjustments per second. They're compensating for wind. They're correcting for tiny navigation errors. They're balancing a 70-meter steel cylinder on a column of fire. If one engine hiccups during those final seconds, the entire catch sequence can unravel. The reliability improvements in V3's engines aren't just about making flights more successful. They're specifically about making the last 6 seconds before catch bulletproof. Because those 6 seconds are everything. Mechazilla gets an upgrade, and it's more important than the booster. Most of the attention around Booster Vive 3 focuses on the rocket itself. But there's a parallel story happening on the ground that's just as important. Mechazilla, the launch tower's catch system, has been completely overhauled. And the most significant change is one that most people completely overlook. The hydraulic actuators are gone. In their place, electromechanical actuators. For non-engineers, here's the difference. Hydraulic systems use pressurized fluid to generate force. They're powerful and reliable in static applications. But they have inherent lag. When you send a command to a hydraulic actuator, there's a brief delay while pressure builds and fluid moves. In most industrial applications, that delay doesn't matter. In a rocket catch, it absolutely does. Electromechanical actuators respond to commands at the speed of electricity. No fluid dynamics, no pressure buildup. Just command sent, arm moves. The practical result? Mechazilla can now begin closing the chopsticks earlier in the catch sequence. The arms can respond to real-time positional data from the booster faster than ever before. And if the booster deviates slightly from its planned descent path because of a wind gust, an engine adjustment, a navigation correction, Mechazilla can compensate in real time instead of lagging behind the problem. There's another physical change that deserves attention. The chopsticks are shorter now. Shorter chopsticks means lower rotational inertia. Lower rotational inertia means faster movement for the same amount of force. The arms can now swing into catch positions significantly faster than before. Combined with the wider initial opening, which gives the booster more room for error on approach, and the earlier closing capability, SpaceX has effectively made the target bigger while making the catcher faster. That's not incremental improvement. That's a completely different system wearing the same name. The timeline, and why the next catch could happen with no warning. Here's where things get genuinely urgent. SpaceX President Gwynne Shotwell made a statement that went relatively under the radar but should have set off alarm bells across the aerospace community. She said major milestones could arrive within months of Flight 13. Months. Not years. Months. Now let's map out what that actually means. Current expectations suggest Flight 13 follows a mission profile similar to Flight 12, testing the booster's return sequence, collecting data on the new Raptor performance, validating V3's aerodynamic behavior. Flight 14 is where things get interesting. Current indications point toward a more comprehensive orbital mission, potentially pushing the first ship catch attempt to Flights 15 or 16. But booster catches are expected to return before ship catches become reality. Why? Because of a logic that's almost poetic in its simplicity. Catching ship is the ultimate prize, but it's also the highest risk maneuver in the entire program. So before SpaceX attempts to catch ship, they need absolute confidence in the catch system itself. And the only way to build that confidence is to catch booster Vive 3, repeatedly, reliably, routinely. The booster is the proof of concept, ship is the graduation, which means a booster catch attempt somewhere between flights 13 and 15 isn't just possible. It may be the entire point of those flights. And here's the detail that should make you pay very close attention right now. SpaceX doesn't announce catch attempts in advance. There's no press release that says next flight will attempt a catch. The catch decision gets made based on vehicle readiness, weather, and mission parameters, often days or hours before launch. The next catch attempt could be announced with 48 hours notice, or less. The numbers that prove why this is the most important catch in history. Let's put some numbers around what's actually at stake here. A single super heavy booster costs SpaceX an estimated $50 to $80 million to manufacture. Each one takes months of precision welding, assembly, and testing. If SpaceX loses a booster, as they did in Flight 12, that's not just a failed recovery. That's tens of millions of dollars falling into the ocean. Now consider SpaceX's stated goal: airline-like operations, regular, frequent flights, eventually daily launches. At current manufacturing rates, that goal is mathematically impossible. You can't fly daily if building one booster takes months. Reusability isn't just a nice feature. It's the entire economic foundation of the Starship program. Every booster catch is worth months of manufacturing time. Every successful recovery is tens of millions of dollars that don't have to be spent building a replacement. And every flight that reuses a previously caught booster is proof that the system actually works as advertised. The Falcon 9 gave the world a preview of this logic. SpaceX has now launched individual Falcon 9 boosters over 20 times. The same booster, caught, inspected, refueled, relaunched, 20 times. The economic advantage that created? Competitors are still trying to catch up, and most of them haven't. Booster Vive 3 is the Falcon 9 moment for Starship, the point where recovery stops being a demonstration and starts being a business model. But there's a twist in this story that very few people are talking about. The twist, the real reason Flight 12 failing was actually good news. Here's a perspective that might seem counterintuitive. Flight 12's failure, the booster that didn't make it back, may have been exactly what SpaceX needed. Not because failure is acceptable, but because of what that failure revealed. When Flight 12's Raptor engine failed early in the flight, it triggered a cascade. The boost back burn became irregular. the landing burn was delayed, and engineers got a complete, unambiguous picture of exactly how the recovery sequence breaks down under engine anomaly conditions. In aerospace engineering, there's a concept called failure mode mapping. You need to understand not just how a system succeeds, but exactly how and why it fails. Flight 12 gave SpaceX a complete, real-world failure mode map for the boost back and landing sequence. Every algorithm that didn't work correctly got flagged. Every sensor reading that showed unexpected behavior got logged. Every timing discrepancy between the planned and actual sequence got documented. That data, the failure data, is arguably more valuable than 3 successful catches in a row. Because successful catches tell you the system works when everything goes right. Flight 12's failure told SpaceX exactly what needs to be fixed for the system to work when something goes wrong. And rockets, by definition, will occasionally have things go wrong. V3's upgraded navigation algorithms are a direct response to what Flight 12 revealed. The improved engine reliability targets specifically address the cascade failure pattern that Flight 12 demonstrated. Even the electromechanical actuator upgrade on Mechazilla, which allows faster response to positional deviations, was influenced by analysis of what would have happened if Flight 12's booster had made it back, but arrived slightly off target. SpaceX didn't just build a better booster after Flight 12. They built a booster specifically designed to survive the exact failure mode that Flight 12 exposed. That's not damage control. That's engineering at its highest level. The bigger picture, what a successful V3 catch actually unlocks. Let's zoom out for a moment because the booster catch isn't the end of the story. It's the beginning of a completely different story. Right now, every orbital launch system on Earth, every single one, is partially expendable. Even the most reusable rockets in existence discard their upper stages. Starship is designed to change that equation completely. If Booster Vive 3 can be caught and relaunched reliably, and if Ship can subsequently be caught and relaunched reliably, SpaceX will have created something that has never existed in the history of spaceflight, a fully reusable orbital launch system. Not partially reusable, fully reusable. The implications of that aren't just technical, they're civilizational. Currently, launching 1 kilogram to low Earth orbit costs approximately $2,000 to $3,000, even with Falcon 9's reusability. SpaceX's target for fully reusable Starship is below $100 per kilogram, potentially far below. That's not a 10% improvement. That's a 30 times reduction in launch costs. At $100 per kilogram to orbit, space stations become affordable for universities. Mars missions become economically viable. Satellite constellations that currently require billions in capital become routine infrastructure projects. The catch isn't about recovering a rocket. It's about making space economically accessible in a way it has never been before. And Booster Vive 3 is the first step in that chain. But here's the detail that keeps aerospace analysts up at night. And it has nothing to do with the technology. The competition problem, and why everyone else is running out of time. SpaceX isn't developing Booster Vive 3 in a vacuum. China has been watching very carefully. In fact, and this caused genuine laughter in certain SpaceX circles, China recently tested their own version of a Mechazilla-style catch system. The attempt didn't go particularly well, but the fact that it happened at all tells you something important. China's space program understands exactly what SpaceX is building, and they understand that if SpaceX achieves full reusability before anyone else, the commercial launch market becomes essentially inaccessible to competitors for the next decade. Blue Origin is trying. Their New Glenn rocket is operational, with its own booster recovery capability. But New Glenn is not designed for full vehicle reusability. The upper stage is expendable. The cost structure is fundamentally different. The European Space Agency is developing Ariane 6 with partial reusability concepts, but the timeline stretches into the late 2020s at best. United Launch Alliance, one of the most established names in American aerospace, is developing Vulcan Centaur, which has no booster recovery capability at all. The competitive landscape is stark. SpaceX is approximately 5 years ahead of its nearest competitor in reusable launch capability. If Booster Vive 3 catches work, and if Ship catches follow, that gap doesn't close. It widens. Every competitor knows this, and the pressure it creates is immense. Which is why the next catch attempt isn't just important for SpaceX. It's a milestone that will define the competitive structure of the entire space industry for the next 20 years. Here's the part that requires intellectual honesty. Booster Vive 3 is the most capable Super Heavy ever built. The upgrades are real. The engineering improvements are significant, but aerospace is unforgiving, and several serious challenges remain. The cryogenic fuel systems, the tanks and pipes that hold liquid methane and liquid oxygen at temperatures hundreds of degrees below zero, operate under immense pressure. A small leak in the wrong place, at the wrong moment, can trigger an explosion that makes Flight 12 look mild. SpaceX has made significant progress in leak prevention, but cryogenic systems are inherently complex, and complexity creates vulnerability. Then there's the engine maintenance challenge. Some of V3's simplification efforts have actually created new complexities in the refurbishment process. In certain cases, accessing engine components for repair now requires cutting open sections of the vehicle rather than simply unbolting accessible panels. During development, that's acceptable. Engineers are learning, iterating, improving. But for the airline-like operations SpaceX is targeting, cutting open your rocket between flights is not a viable maintenance model. The refurbishment process must eventually become as routine as changing an aircraft engine. SpaceX knows this. They're working on it. But it's not solved yet. And then there's the weather. Boca Chica, Texas, where Starbase is located, sits on the Gulf Coast. Gulf weather is unpredictable. High winds, sudden storms, and atmospheric turbulence don't care about launch schedules. The expanded catch envelope that Mechazilla's upgraded arms provide helps. But there are wind conditions beyond which no catch should be attempted. The navigation algorithms must now be precise enough to abort a catch attempt in real time if conditions deteriorate below safe thresholds, without losing the booster entirely in the process. That's a software challenge as much as a hardware challenge. And software, as every engineer knows, has a talent for failing in ways nobody anticipated. These aren't reasons to doubt Booster V3. They're reasons to understand that the next catch attempt, whenever it comes, carries genuine stakes. SpaceX doesn't need the next catch to be perfect. They need it to prove that V3's improvements work as designed under real flight conditions. That's the standard, and it's a high one. The moment everything changes. Here's what a successful Booster Vive 3 catch actually looks like, not just technically, but in terms of what it means for the entire program. The moment those electromechanical arms close around V3's fins, and the booster comes to rest, suspended above the launch mount, SpaceX will have demonstrated something profoundly important. Not just that catching rockets is possible. They proved that in Flight 8. But that catching rockets is repeatable, reliable, systematic. That's the difference between a trick and a technology. A trick is something you do once under perfect conditions and never attempt again because you're afraid of failing. A technology is something you do repeatedly, refine constantly, and eventually make routine. Flight 8's catch was a trick, an extraordinary history-making trick, but a trick nonetheless, because it wasn't followed by more catches. It was followed by 4 flights without catches, including 1 catastrophic failure. A successful Booster Vive 3 catch, especially if followed by another catch on the subsequent flight, would transform the catch from a trick into a technology. And once that transition happens, the ship catch becomes not a question of if, but purely a question of when. And if ship catch succeeds, every rocket program on Earth will need to answer a very uncomfortable question. How do we compete with a fully reusable orbital launch system that costs a fraction of what we charge? Most of them don't have a good answer. SpaceX does, and it starts with the next time those giant chopsticks move into position. That's the full picture of what SpaceX just revealed, and why Booster Vive 3 isn't just another upgrade. If this breakdown gave you clarity, hit like, share it, and subscribe to the Space Brief. Drop your thoughts below. I read every comment.